Okay, so from this point on, I'm gonna have to turn that off. Okay, how's that? Okay, we have good audio. So from this point on, you will find a recording of this lecture on YouTube, and it'll be available. It's available even now, the parts that we've done, and it will be available as soon as class is over. So we've covered the first 3 points, and I'm going to talk as much as I can now about the types of data and important types of graphs. Spent a fair bit of time on introduction, so I might not quite get all the way through it, but that's okay. If we don't, I'll finish it up tomorrow or next week. So if we're going to start from square one, I should tell you what statistics is. It can be categorized into these 3 parts: design, which is what you do before you even collect data. You plan out your experiment, and you would typically have your analysis in mind even at that point as you decide what type of data you're going to collect and how you're going to collect it. Experimental design is a big part of what biostatisticians do. If you're a consulting biostatistician, people come to you and ask for consultations when they're planning their study, and they want to know how many participants they need, how they should sample their pool of participants, what type of data they should collect with them in order to answer a specific hypothesis or research question. Very important part of being a biostatistician. Description, which is what you would see often in newspapers, the graphics, the numeric summaries, also very important part of statistics. This is one of the big ways of communicating data to other people, of taking large amounts of complex data, synthesizing it, and presenting it in a digestible format that's appropriate for your audience. And then inference is the part where you make decisions based on hypotheses, where you take information from a limited number of people or records and use it to infer something about a whole population. And we're going to go, this class is fairly heavy on description and inference. Sometimes there are whole classes on experimental design. We'll do a little bit of it, but we're basically going to start with description and move on to inference in this class. And as part of the inference, we'll do just some bits of experimental design or study design. Statistics has been around for a very, very, very long time. Even much longer than science as we think of it has been around. Most people would say modern science is something like, the idea of hypothesis-driven science is not much more than 150 years old or something like that. Evidence of people using statistics goes back to at least 450 BC, doing things like calculating averages, as people intuitively understood that by measuring something multiple times and averaging it, you would get a more reliable measurement of something than by just observing it once. So statistics is old and it's useful. It's been developed for a long time. Let's start with some definitions. And you're going to hear these over and over. The population is an entire group of interest. So it might be all people, as in the whole world. It usually isn't. It is often something more specific than that, such as American adults or even just residents of New York. But the point is that it includes everyone who you're interested in for a particular research question. The population is often too many people to observe, and so we study samples. And a sample is some subset of that population. We typically will use random samples of the population and take enough that it's something manageable, an amount of data that we can collect and learn something about the entire population from. So in this example here, London being voted one of the world's favorite cities in the largest ever global survey of its kind. They covered 18,000 people in 24 countries. And I don't know, I picked up on this because I was new to New York, and noticed that it's actually just Europe's top city, London. But that was in a London newspaper, and New York was a favorite for a couple of things, for doing business, and overall favorite. So what is the population that they're going after here? But what's okay? That's not the population is the group that they're making a statement about.
People like
yeah, so these are, so I've heard two possible answers. It's the entire world, or it's these 24 countries, and you can think of it in different ways. I think that they're trying to say, just based on this statement here, the world's favorite cities, to me that means that their population is the world. Now, they've only sampled 24 countries, but I would say that that is a sample of countries in the world that they've done because it wasn't practical to ask the survey in all countries of the world. So whether or not that's a representative sample of all the countries in the world, we don't know. But I think in this case, they're not just trying to say something about those 24 countries, they're trying to say it about the entire world. So what's the sample and what's the population really depends on the kind of statement that you want to make before it depends on the way you collected your data. Does that make sense? Now, in some occasions when you actually can observe everyone in your population, we call that a census. And a census, hi there, you want to just grab, are there any more handouts left? Here's one. So when you observe everyone in the population, it's a census. And every observation, whether it is a sample or a census, one observation we call it an observation, or we also call it a record. Descriptive statistics is just that. It's taking something complex and trying to make it so that your audience can, so that you can learn something about it and your audience can learn something about it. This is a nice famous graphic about the conquest of pestilence in New York City. It's the cover of one popular statistics textbook. And it's nice because it was done before computers. This is all hand-drawn. And it is showing on our x-axis, our independent axis, it is showing time. This is year. And on the y-axis, the dependent axis, it's showing deaths per 1,000 population. So that's a mortality rate, something that we'll talk about a bit more later. But you can just watch it change over time. And for every one of the spikes here, they have made a little annotation there about what was the cause behind that spike in mortality. So it's an extremely informative graphic. And here on the right side, they're just listing the same label again. Graphics aren't the only type of descriptive statistics, and I'll talk about some other ones as well. But inferential statistics, so that's where we want to make inference about a population from our sample of the data. Obama approval little changed in 2014. So this is based on several different samples. These are 4 different corporations doing different surveys. They have their own sampling methodologies. They're all trying to represent here. Let's see, it says polls testing Obama job approval. RVs equals registered voters, others based on adult population. So what's the population here? Mm-hmm. Yeah, so some of them are. These two, CBS News and NBC Wall Street Journal, would be the American population. These ones that say RVs would be only the registered voters. And if it seems I'm belaboring a little bit the population sample difference, it's because it's actually more complicated than it sounds, and than it seems at first. It's not complicated, and I'm going to try to make it not complicated, but it's a very common source of confusion as we start getting into calculating things and summarizing things, and it becomes very important to keep in your mind whether the numbers that you're talking about right now, whether these are numbers representing the sample or the population. And so I'll be keeping this point very clear throughout the course. Yes?
Just a question about the graph. If only two are registered voters and the other two are just American population, are you able to compare these?
So the question is, are you able to compare these? Because two of them are registered voters and two are the adult population. It's a very good question, and it's not clear up front whether those would be comparable. It looks from this graph like they're pretty comparable, but that would be a question of inference, and that's a question that that we could ask using inference to say whether the population of registered voters has a different approval of Obama than the overall population. And using these data, that is something a question that we could ask and make a conclusion on. By eye, it looks like they're comparable, but looks can be deceiving. I don't think they're too deceiving in this case. I would say, yeah, they look pretty comparable. The kinds of questions that we want to answer around this are how great is the uncertainty? I mean, you see these 4 lines here. One of those lines doesn't give you any measure of uncertainty. It's just a single data point there. So, we don't know how many, maybe one of these polls, someone just asked 2 people and gave a percent. Probably they did more than that, but we don't know. We don't know how much uncertainty is on there, and we also, well, we're never going to know all of the sources of uncertainty, but we're going to think about the sources of uncertainty, and some of them we can quantify. When it comes to certain things like sampling bias that we'll talk about, those are very hard to quantify their effect on the results. But random sampling variation is something that we'll spend quite a bit of time trying to quantify how much of an impact that has on results like this. If we went out and did the exact same study again, how much different would we expect the result to be, for example? Just a few other examples, common things we use statistics for. Does an experimental treatment for cancer work? That would probably be an inferential type of question. Is cycling in the city becoming more dangerous? Could be both description and inference. Do public health issues differ across the city? Another question that could involve both description, maybe mapping things out across the city, as well as inference. Inference tends to be the yes or no questions, and description tends to be, the describing things, showing graphics. And if you have other examples, especially from your own work and own interests, I think we'll all be interested in hearing them. I know I will be. I'm going to review the types of data, and or introduce 4 types of data. There are different ways to classify data. I'm going to use this, and this is going to be a basis on which you're going to decide what methods to use. The first step in analyzing data, and one of the things that I find really really distinguishes between people who are very accustomed to analyzing data and people who are not. If you're someone who's very accustomed to analyzing data, the very first thing you want to know is what type of data do you have. And when I'm talking to another data analyst, we get through that very quickly. They'll say, you know, the dependent variable is this type, we have predictors of these types, and then immediately I have some reasonable base level understanding of the data set. So here they are, nominal, ordinal, discrete, and continuous, and I'll talk about each of those. First, nominal data, which includes binary or dichotomous, and also includes categorical data. So binary dichotomous, that just means that there are 2 possible levels, male, female, alive, dead, just things where your questionnaire or something about it means that you're only allowing for 2 levels. Now, notice I put a 0 and a 1 here. This is what happens in software when you're analyzing nominal data. It will recode them as numbers, but the reason we call it nominal data is because those numbers aren't real. They're a convenience used by software, but these are only sort of nominally numbers. They're really words, they're states of being. They're not numbers that you could use mathematics on, things that would make sense to add, subtract, do that sort of thing. And categorical is just nominal data that has more than 2 levels, such as blood types. So A, B, AB, or O could be recoded as 0, 1, 2, 3, 4, even though those numbers wouldn't mean anything. There's no natural ordering of nominal or categorical data. And they're only nominally numbers. So ordinal data is almost like nominal data, except that there is an order to the data. They're still not really numbers. So as an example, this Karnofsky performance scale that rates how mobile a patient at a hospital is, from fully active to less active, less mobile, to completely non-mobile or disabled. These have a ranking from the most active to the least active, but they're not really numbers. Again, they're nominally numbers, but they are ordered. So the order is important, but the magnitude is not. It makes no difference. The difference between 0 and 2 here is not the same as the difference between 2 and 4. So the subtraction doesn't make any sense, multiplication doesn't make any sense, only the order matters. As an example of that, another type of ordinal data would be people's rank in a running race. So you might have your first and second place finishers that are in a photo finish almost the same, and then your third runner is way, way back. So the difference between 1 and 2 is not the same as the difference between 2 and 3, but the order is there. And that would be an example of rank data if you're talking about the rank in a race, and it's one important type of ordinal data. This is not rank data. Order and finishing a race would be rank data. The top 5 causes of death in the United States. These are numbers, total numbers, and they're ranked here. So heart disease is the #1 killer, or it was in 2010 at least, and I think it still is. Number 2 being cancer, still very close. And then number 3, way back, chronic lower respiratory disease behind heart disease and cancer. Okay. Now, discrete data is the first type of actual numeric data. These really are numbers. And what distinguishes them is that they are integer data or count data. So back in this leading causes of death, the numbers here, because they're counts, are discrete data. Now, I'm not going to belabor the differences between discrete and continuous data generally, especially in a case like this where the numbers are large. It really doesn't make any difference in this case whether it's discrete or continuous when you're talking about hundreds of thousands. If you're talking about, you know, fewer than 10, then it might make a difference whether you're whether it's continuous or discrete. But in general, discrete just means that only certain values are possible, like the number of people who died of heart disease. And I only show this because here I am, it is shown as a number per 100,000. So these are adjusted death rates. It's still a discrete variable, even though in general this could be decimal. But to me, at that point, it's kind of splitting hairs whether it is discrete or continuous. The important thing is that it's a number and the rules of arithmetic apply to it. So yeah, these are standardized per 100,000. And I only point out here that there are fluctuations in these 4 and 5 positions to give that as an example of likely uncertainty and random fluctuation in the number of deaths due to these diseases. So we have stroke, lower respiratory disease, and diabetes all taking place or taking turns in those 4th and 5th positions. So if you were to think of 1 year as being a sample of all of the victims of these diseases over a large amount of time being the population, then you would have sampling variation from year to year, just due to the people who happened to be around that year and to random events. So, and again, discreteness becomes really unimportant when you have a lot of possible values, like thousands of deaths. Finally, continuous data. So, continuous data are things that have decimals and any value is possible. So, time, weight, length, mass, and you can rightfully point out that you know, maybe time is measured in seconds or hundreds of seconds, and your timepiece only takes discrete measurements. You're right. That's where this distinction between continuous and discrete variables gets a little bit fuzzy. But these are kind of the classic continuous variables, because at least in theory they could be any value. And they may be bounded. For example, mass is always greater than 0, length is always greater than 0, or they may be unbounded, some things between minus infinity and infinity. So with these, both the magnitude of it matters and arithmetic applies. You can add, subtract, multiply, divide, and do any sort of arithmetic. We have a few more minutes to talk about summarization of data. And it's something that, I don't know if it gets full, I think it's proper due course in many courses. To me, summarization of data is the first thing that you do when you get a data set in order to understand your data set and to try to build an intuition for what it has to say about your question before you set out doing statistical tests, because oftentimes your intuition is good if you produce the right summaries, and it will help you keep you from making mistakes if you do an analysis and get something that doesn't match with what you saw in your summarization. And there are lots of options for every data type and combinations of data types. I'll cover a couple that we use for nominal and ordinal data. The frequency table, also called contingency tables, all this is counting up the different values that occur and providing those total numbers for each variable. It is an alternative to this, the pie chart. Can anyone tell me what's wrong with the pie chart?
87%, and graphic as 50%.
Yeah, so as you pointed out, the graphic shows 50% and the numbers show 87%. But actually the first problem here is that they used a pie chart, in my opinion. As biostatisticians, we never use pie charts. So I don't know, in your final projects and that, don't use pie charts. They're okay for newspaper articles. They're nice because they look like pies, but they're not actually that informative. The second problem is, yes, that the numbers don't match up with the numbers don't match up with the graphic. And we can tell that because we basically have here a frequency table, the 8713, and we also have the graphic. This is what so-called one-way frequency tables look like for a single variable, and all it is a count of your number of records that have each value of your nominal or ordinal variable. So this first one, this is a binary or dichotomous variable. The second one would be a categorical or an ordinal variable because it's mild, moderate, severe, and does have an order. What you can show in a frequency table, you can also show in a bar chart. And a bar chart is our preferred alternative to the pie chart. The reason that that statisticians and I think usually epidemiologists prefer a bar chart is because it's more informative. Because you can actually look across any one of these bars and read the number, and you can very easily compare to see which is higher than the other, which is very difficult to do with a pie chart. So when we have two nominal or ordinal variables, we can make a two-way frequency table, which this is an example of. So instead of just having one row or one column, as before, we have rows and columns. And it's just adding up the number of records with each pair or each possible combination of these two variables, treatment and pain. If you have three variables, then you would have to do this as a series of two-way frequency tables. These sums that I've put here in the margins, these are called marginal totals. And that's a terminology that I'll come back to. In this case, they're marginal totals. I'll also talk about marginal probabilities, which is something that sounds fancy, but is actually simple. That would just be, there are 100 patients here, it would just be each of these numbers divided by 100 to provide marginal probabilities instead of marginal totals. Marginal, that's it. We just say that because you write it in the margins of a frequency table. Keep on getting a little bit ahead of myself, forgetting to advance the slides, but there they are, the marginal totals and the marginal probabilities, being the probabilities being 50 over 100, 0.5. So the marginal probability of having received the treatment in this fictitious clinical trial is 50%. And the marginal probability of experiencing mild pain is 20. And that's regardless of whether you receive the treatment or the control. So again, anything that you can display also in a two-way frequency table, you can also display in a bar chart. And one way is with this so-called stacked bar chart, where we're showing treatment and control as separate bars, and then shading differently the level of pain reported for each of them. So you can look at this and see, okay, there are 50 each who receive treatment and control. In the treatment group, it's equal, more or less, numbers of people reporting mild, moderate, severe pain. And in the control group, there's a much bigger chunk of people reporting severe pain. So it's a very descriptive, compact description. There's no equivalent of this in pie charts. You can't do a two-way pie chart. The other type of bar chart I should mention that could be used here, but I didn't put in, is the sort of side-by-side bar chart, where instead of these being stacked, this would be 3 bars side by side. Also a valid way to do it. It just shows something different. It's a little harder to count the totals when you do a side-by-side bar chart. I should note also that you could, of course, do this the other way. Just like you can switch the rows and columns of a frequency table, you can switch the rows and columns of a two-way bar chart, just by the way, the order in which you enter your variables into the software. So we could have had 3 bars for mild, moderate, severe, and showed the number of treatments and controls for each of those levels of reported pain. Okay, we're getting short on time here, so I think I might just finish up with this, with the summarization of discrete and continuous data in the next class. Are there any questions about what we've done so far? And no, I will come downstairs and join you in the lab, so you have a chance to ask me more questions or talk to me down there as well. All right. If not, thank you, and I'll see you down in 5 or 10 minutes down in the computer lab C06. If you're not sure where it is, you can wait and go down with me. It's down in the basement of this building.